Radio astronomy has altered the way we view the universe and dramatically increased our knowledge of it. Our passion for learning about what lies beyond the stars has driven scientists and engineers to build extraordinary devices for looking into distant galaxies. The National Radio Astronomy Observatory began building the Very Large Array, or the VLA telescope, in the 1970s. The VLA is a multi-purpose instrument, an array of 27 antennas that help scientists investigate a variety of astronomical objects, including radio galaxies, quasars, pulsars, remnants of supernova, gamma-ray bursts, radio-emitting stars, the sun and planets, astrophysical masers, black holes, and the hydrogen gas that constitutes a large portion of the Milky Way galaxy. On the plains of San Agustin in central New Mexico, the Carl J. Jansky Very Large Array is the world's premier radio telescope observatory. In 2011, a decade-long upgrade project resulted in the VLA expanding its technical capabilities by replacing old electronics with newer state-of-the-art equipment. The scientific community and the public were asked to suggest a new name, and in 2013 it was renamed the Carl G. Jansky Very Large Array to honor the scientist credited with the discovery of radio waves from the Milky Way. The VLA certainly lives up to its name. Each antenna is 94 feet tall, and the dishes are 82 feet in diameter. They're spread out in a Y form 13 miles in different directions. Combined, they make a massive synchronized system that monitors a unique kind of light. Multiple linked telescopes used in an array is referred to as aperture synthesis. Our eyes see only a small sliver of the light that reaches us from space because objects in space emit light across the entire electromagnetic spectrum. At the long wavelength end of the spectrum is radio light. Because its wavelengths are so long, making sharp pictures from radio light requires a telescope that is miles wide. This invisible light reveals the birth of stars, the secret of ancient galaxies, and the presence of black holes. Before the 1930s, optical telescopes were the only tools astronomers had. In 1932, Carl Jansky made the pivotal discovery of radio waves coming from the Milky Way galaxy. The ability to record and study radio waves has allowed for substantive increases in astronomical knowledge. Since its completion in 1980, the VLA has been making astounding discoveries, from water ice on Mercury to the remarkable jets of elliptical galaxies, and the physics behind gamma-ray bursts, the most powerful explosions in the known universe. 50 miles east of the array is the town of Socorro, where the VLA's scientific center is located. This is where astronomers take the information from the VLA and study the latest chapters in the story of the cosmos.
As an astronomer, I spend a lot of my time sitting at my desk in front of a computer. And while we get observations from telescopes like the VLA, most of the time is spent reducing that data, analyzing that data, and trying to figure out what's going on.
Many astronomers find objects that can become a career-long focus.
Henize 210 is visible in the south, and it's in the constellation Pyxis, and it's about 30 million light years away. It's a very small little galaxy, but it's a hotspot for star formation. There are these young, massive star clusters forming today, and these are similar to the types of clusters that were formed back in the early universe.
The dwarf galaxy Henize 210 is 10 times farther away than the most distant object we can see with the naked eye. Its secrets are hidden behind gas and dust, but radio waves have been escaping and can be captured by the VLA. On Earth, these extremely weak radio waves must be distinguished apart from thousands of other man-made radio interference. In a custom-built test chamber, VLA engineers measure radio signals given off by everyday items, such as this cell phone.
check what we're seeing on the spectrum analyzer screen.
Oh yes. So you can see we're getting some really strong RFI here in the 2.4 to 2.5 gigahertz range.
Even with no service, the radio emission is some 20 trillion times stronger than the most powerful radio sources in deep space. Back at the telescope location, there are engineers that tackle general maintenance routines. Every few months, they climb 30 feet to the apex for critical installation and maintenance of the P-band receivers. These low-band receivers are especially important for detecting invisible hydrogen gas in the early universe, the main ingredient of future stars and galaxies. Regular upgrades like these are important to keep the telescope running with the newest technology. The entire array has recently gone through major upgrades. The original array, completed in 1980, was rebuilt from the inside out. In 10 years' time, nearly all of the electronics inside the telescope were replaced, essentially creating new instruments with old skeletons. At the center of the VLA expansion project was the development of a new supercomputer called the Correlator. It is housed in a meticulously controlled cleanroom environment. This powerful computer turns 27 radio dishes into one enormous telescope. Massive data streams from each antenna are fed to the control building, where the correlator increases the telescope's capabilities by more than 2,000 times. Not only do the dishes adjust and move to track objects in the sky, they also move throughout the array itself. Custom-built 90-ton flatbed locomotives are used as antenna transporters. Engineers carefully line up the locomotives under the telescope's triangular base. Once they're secured, 230 tons of steel is hoisted into the air, and the antenna is slowly transported to its destination. They will not move an antenna if winds exceed 20 miles per hour. And maximum transport speed of the locomotives is 5 miles per hour. The upgraded antenna is carefully mounted and secured in its new home in the vast array. But the placement isn't permanent. Approximately every 4 months, the antennas are moved into one of 4 different configurations, A through D. Each configuration changes the depth and detail the telescope sees. Combining data from each of the 4 different configurations deliver the best image quality. When the antennas are packed together into the D configuration, the telescope detects faintly glowing clouds of gas. At their furthest distance from each other, in the A configuration, they capture the finest details of the radio universe. With several more adjustments, astronomers are ready to study the light of the dwarf galaxy Henize 210.
Copy that. We're getting ready to run the C-band observation.
This light from Henize 210 has traveled through gas and dust for 30 million years, and 150 quintillion miles to reach us. An entirely new catalog of human knowledge is captured and recorded.
Our team just finished reducing all of our new data, and we have some spectacular images now. And we can do a very detailed comparison between the optical data from the Hubble Space Telescope, the infrared data from the Hubble Space Telescope, and now the radio data from the VLA. We found this source of radio emission that looked very much like it might be a supermassive black hole in this tiny little galaxy.
Deep in this galaxy, 30 times smaller than our Milky Way, this supermassive black hole is feeding on the surrounding gas.
This has implications for our understanding of the evolution of galaxies and their black holes, and even the formation of the first black holes back in the early universe.
Careers in astronomy can be extremely challenging, but highly rewarding. Students interested can research through NASA, the NRAO, or the National Optical Astronomy Observatory. A keen focus on physics, math, and astronomy courses is the best place to start. The ability to detect and understand radio frequencies has given astronomers the chance to gather information about some of the most important discoveries related to the birth of stars and galaxies. As this technology advances, we can expect the future to be filled with exciting new discoveries about the building blocks of far-off galaxies.